I will go without video today. Okay. Good evening, everyone. Sorry for the delay. Mahesh, is this audible? Okay, fine, great. There was some internet issue. There was some internet issue in the NPTEL studio, I think. So sorry for the delay. So I see that there are a few people here. If you have any questions, why don't you ask that first? I've just put in the topics for your reference. So we talked about link design this week, and we said, and whatever we did this, the link design was for an on-off keyed system, for a coherent system. It's something similar, but you don't really do a rise time budgeting for coherent system, simply because you do the rise time or the dispersion compensation in the digital signal processing domain. So you don't have to do a rise time budgeting in case of a coherent system. What we talked about rise time budgeting and loss budgeting, that will be for the OOK system. So let me just put it down for coherent systems. We do have to do loss budgeting. In terms of if it's a long link, you have to do the OSNR budgeting, which you are doing in this case also. And you rise time is taken care in, or let me not call it rise time and say that the dispersion compensation happens in DSP, in the digital signal processing domain. So we really don't worry about dispersion compensating fibers, etc. That's what happens in a coherent system. And we gave some, I gave you some specific case studies on how you evolve from a simple passive optical link to systems which have amplifiers. How do you calculate the degradation that is put in by an amplifier in a long haul system, and so on. Then we spent some time on understanding the dispersion compensation. And as I said earlier, we could do it in the signal processing domain, but if it is an on-off keyed system, we typically don't use a signal processing. We use dispersion compensation fibers. And I also briefly told you how to calculate the length of the fiber that needs to be used for dispersion compensation. And then we just started discussing nonlinear effects. So we just touched upon cell phase modulation, and we would talk more about other nonlinear effects in week 10. But they have to be taken care of if your input power is large. But typically you try to avoid the nonlinear effects by launching smaller powers into the fiber. Any questions related to this week's content, please type in the chat window. In the meantime, I will start pulling out the assignment questions. Question 1 is make the power budget and calculate the maximum transmission distance for a 1310 nanometer system operating at 100 Mbps using an LED for launching 0.1 milliwatt of average power into the fiber. So one of the tips for you is to actually convert everything into dBm, into decibel scale, so that calculations become simpler. So, in fact, this week's assignment is fairly simple and straightforward. So, because most of the assignment kind of questions, we did it in the class. So, you want to make the power budget for a link. So, the first thing to do would be to draw a diagram. Always try to draw a diagram of what you're trying to, what kind of link that are you planning to build, and then it becomes very easy. So, it says that maximum transmission distance for a 1310 nanometer. So you have a transmitter, you have the receiver. You basically want the distance. This is the link length is what you want to calculate. What is known about the transmitter system? Transmission, you have 1310 nanometer. That is something that you know about the transmitter. Operating at 100 Mbps. So that also you know for the transmitter. And LED is launching 0.1 milliwatt of power. So, so lambda is this. This is bit rate. And power is 0.1 milliwatt, which is 1 milliwatt is 10 dBm. So 0.1 milliwatt is minus 10 dBm, right? Assume 1 dB per kilometer for fiber loss. So you have a certain fiber loss. And that is, so you have the fiber in between. 1 dB per kilometer is the loss in the fiber, and 0.2 dB splice loss for every 2 kilometers. So which means that after every 2 kilometers, so the fiber is not just one piece of fiber. You have a 2 kilometer fiber, then you have a splice, then you have another 2 kilometer fiber, then you have a splice, and then again you have another 2 kilometer fiber, and so on, right? So this splice loss is given to be 0.2 dB. Now this 0.2 dB is in every 2 kilometers. So if I were to do it, club it along with the fiber loss, I could just say that this is 0.1 dB per kilometer. Every kilometer, I would have to take a hit. Even though the splice is not at every 1 kilometer, you can imagine that if you want to do a per kilometer calculation, it becomes easier if you find the loss per kilometer. Okay, and then there is a connector loss of 1 dB at the transmitter and the receiver. So the transmitter has a connector. So there's another loss here. And similarly at the receiver, there's a connector. And so there is a 1 dB here loss, and there's another 1 dB here, right? So this plus a 2 dB. So this is all the loss in the system. And now what happens at the receiver? At the receiver, what is given? 100 nanowatt sensitivity of the photodetector. So P received power, average received power is 100 nanowatt. 100 nanowatt is 0.1 in terms of microwatt. So I can say that 0 dBm is 1 milliwatt. So 1 microwatt would be minus 30 dBm, because you went 3 orders of magnitude down. So 0.1 microwatt is one more order of magnitude down. So this number is minus 40 dBm. This is the received power that you get. Okay, so you have information about the transmit power, you have information about the loss, and you have the information about the receiver. Now, how do you set up the link? So it is a 1310 nanometer system. That's a very good information, because if it is 1310 nanometer, we can say no dispersion, because zero dispersion wavelength is 1310 nanometer. So no worry about rise time budgeting, because there is no the question also says that allow for a 6 dB margin, which means that there is a plus 6 dB margin to be added in the loss, so that you know if there is any future splice or anything required, you are allowing for that margin. Okay, so no worry about rise time budgeting, because you are operating at 1310 nanometer, right? That's a good advantage. Now, how do you go back and calculate the budget? I mean, we have solved a similar question in the class. I have shown you how to do that. So first you find out what is the allowed loss. You have a transmit power is minus 10 dBm. You have a receive power of minus power required, minimum required is minus 40 dBm. And so the difference is your allowed loss. So you will have minus 10 minus 40. So, and of course you have a system margin. You can take either the system margin in the loss, or you can take it here in this margin also. So you're having a system margin of -6. So you could do this. And so your allowed loss is 24 dB. Of course, I'm not going to give you this answer, so you have to work it out. So once you know the allowed loss, then you take care of the losses per kilometer. You can, let's say this, okay, this number is 24 dB. So you know that you can have a total loss of 24 dB. Now you know what is the total loss per kilometer for every total loss every kilometer, and also you remember to take care of this 2 dB transmitter receiver splice loss. Subtract, you can divide it by the so it's like this. So you have loss per kilometer plus transmitter loss plus your receiver loss should give you the allowed loss. So you know the transmitter loss, you know the receiver loss. You could actually add the system margin also here if you are not taking care of it here. Let's do that, and then you can calculate what is so loss per kilometer multiplied by the length of the fiber, right? And that will give you the solution of this equation will give you the length of the fiber. So it's actually a simple arithmetic calculation that you need to do. We move on to question 2 now. So I think Vasundhara is also asking about question 2. So we move on to question 2. Let me just reconfirm the question. Question 2 says that what is optical, okay, so there is a system again given. So let's look at that system again. 1550 nanometer optical system has 3 spans of lengths. So again, it's always useful to draw this. You have a transmitter and you know that the lambda is 1550 nanometer. So you know the danger of using 1550 nanometer. You need to consider dispersion. You also know the advantage of using say 1550 nanometer. You don't have to worry, or rather you can use an EDFA to compensate for the loss. It has 3 spans of length, 80 kilometer, 120 kilometer, and 50 kilometer in sequence with amplifiers in between. The transmitter is directly connected to the first fiber of length 80 kilometer. So I have the information that from this you have the transmitter, which is 80 kilometer. And then comes the amplifier. And again, you have a length of fiber that is 120 kilometer. So it's an unequal span link for whatever reason. You have, sometimes you may have to do this because there's already these kind of fiber link that is available, which is already dug and available to you. So sometimes you may end up using unequal fiber link. There's an EDFA, the output of the 50 kilometer also. So here also you have an EDFA. And then it goes through the to the receiver. So you have the EDFA 1, you have EDFA 2, and you have EDFA 3. Fiber attenuation is 0.25 dB per kilometer. So this is the net loss here would be, what else do we know? The signal power from the transmitter is 10 milliwatt. So P transmitted is 10 milliwatt. And as usual, we will write this in dB scale. So this is 10 dBm. Let's write down the loss here. So this is 0.25 dB per kilometer. So I know that per kilometer, if it is 1/4, for 80 kilometer, it will be 20 dB loss. I'm just looking at the bulk loss because that's what this EDFAs are supposed to compensate for, which means that as the power propagates through this, so if I just sketch the power budget here, you started with 10 dBm at the transmitter. At the end of 80 kilometer, you reached a power. So what I'm drawing is power across, distribution of power across the link, power on the y-axis, and the distance along the x-axis. I know that I started with 10 dBm power, and there is a loss of 20 dB here. Okay, so let me just give myself some more space here, right? There's a loss of 20 dB here, which means that after this 80 kilometer, at a rate of 0.25 dB per kilometer, the power would now be minus 10 dBm because there is a 20 dB loss. So the power became this, right? Distributed loss across the fiber. Now, what is this EDFA doing? This EDFA is, if it's a correctly designed EDFA, it provides a gain G1, and that G1 is equal to, it will exactly compensate for this 20 dB. So the EDFA will push this power back to 10 dBm. So the gain of this EDFA G1, we now know that it has to be 20 dB so that it can be brought back to the original power. Now what happens after that? There's a 120 kilometer fiber. So if this is 80, it's slightly longer here. So let's put 120 kilometer here. And after 120 kilometer, let's call the loss here now would be 1/4 of 120. So you have a 30 dB loss in this segment because it's a longer length of fiber, which means EDFA2 has to give you a gain G2, which corresponds to 30 dB. This EDFA has to operate with a slightly higher gain so that it can compensate for this loss. In the power distribution map, how is this going to look like? At the end of 120 kilometer from here to, so this is not 120 kilometer. This separation is 120 kilometer. So this would be 200 kilometer, right? So this is from Z equal to 0. This is 200 kilometer. And you have this second span of length, 120 kilometer. And what is the power at the end of 120 kilometer? It is going down by 30 dB, which means that if this is plus 10, this is minus 10. You started with plus 10 and it has to go all the way down to minus 20. So let's say this is minus 20 dBm here in this line. And at 200 kilometer, it has actually gone down to minus 20 dBm. Now, what the next EDFA is doing is it is actually G2. It is compensating for this power. It is giving you the 30 dB gain so that the power is brought back to 10 dBm. Now, what's the third EDFA? What should be the gain 3 of the third EDFA? Again, it is 50 kilometer. So the loss of this link is 1/4 of 50 kilometer. So this will be 12.5 dB. Which means my G3, it has to compensate for 12.5 dB. So in terms of again, 200 becomes now 250, let's say, after 50 kilometer. And at 250, I will get 10 dBm minus 12.5. So that is minus 7.5. So I have something like this. But the third EDFA is going to compensate and it is going to bring back to 10 dBm. And this is where my receiver is sitting. Okay, so this is how the power map of this link going to look like. Now, the issue is the loss is getting compensated very well. The question is, what happens to the signal to noise ratio? Each of these EDFAs, as we have seen in the class, they keep adding the amplified spontaneous emission. And it is not just the if you look at the signal to noise ratio excursion, that's not going to come back to the original signal to noise ratio. The signal to noise ratio will keep degrading across the link. So the problem given here is related to that. So the first part is what is the optical noise power density at the output of the last EDFA, right? So what is the noise PSD, power spectral density, at the output of EDFA 3? Why are we interested in the output of EDFA 3? Obviously, because that's what is going into the receiver. So if I have a certain noise at the output of the EDFA 3, that noise is what the receiver sees as the optical signal to noise ratio, and hence the SNR is decided by what is the accumulated noise at the output of the third EDFA. So now the question is, how do we calculate that? So I know exactly what is the gain of each of these EDFAs. That's a useful information. Okay, and I can assume that for all fair reasons, this is what do I say? It is a ideal EDFA with a 3 dB kind of the noise figure of the EDFA is not given to you, so you can ideally assume that it is the 3 dB noise figure. Okay, and yeah, there's no noise figure that is given to you. So if you don't have a noise figure given to you, you can safely assume that the noise figure is 3 dB. Okay, so all what you need to do is simply keep finding out what is the power, what is the amplified spontaneous emission power at the output of each stage. So how do I calculate the AAC power? So last time we discussed, we have it here. Here. Probably I don't have it here because this happened in the session on EDFA. I'm sorry, I don't have it here. But the concept is here. Here. The optical noise power is simply the power spectral density of AAC noise, ESD, which is rho AAC, times the optical bandwidth. Okay, so we are going to calculate that. Now, how do I calculate that? This recipe we had discussed in class. Here, we had here. We had said that here is your rho AAC. Rho AAC is nothing but 2 NSP H nu G minus 1 times bandwidth is multiplication here. So rho AAC, that is a power spectral density of AAC noise. So rho AAC, which is power spectral density of AAC noise, we already said that is equal to 2 NSP H nu G minus 1. This is per unit bandwidth, and this, if you can write it in the log scale, you will write rho AAC as 10 log of 2 NSP, which is nothing but the noise figure of the EDFA, plus 10 log of H nu, you know the Planck's constant, you know the value of frequency, plus 10 log. So when you say this G minus 1 here, this is in linear scale. So 10 log of G minus 1, this becomes gain in dB. Okay, and because you can safely assume that in the linear scale, the gains that we are talking of in the linear scale, what does this gain mean? This is 100 times, this is 1000 times, and this is roughly 20 times. So you can safely ignore this one as compared to this number, and then you can directly write this as a gain in dB. So the consequence of this relation is the following. You have rho ASC. This is what we had derived in class also. This is noise figure in dB. So this is the dB relation or log scale relation. So in the log scale, so which means you are calculating this rho ASC of in dBm. Okay, this would be noise figure plus, this is noise figure from here, plus this number. This number we have calculated this number, that is that 158.92, right? So I'll just write it as 10 log of h nu here, right? Plus G1. This is for the AC of the first stage, where G1 is the dB gain, decibel gain of first stage. All right. Now, this is rho ASC for the power spectral density of the first stage. Similarly, you can find out what is rho ASC 2 and rho ASC 3 for the second stage and for the third stage. Mind you, you will get this answer if you do this. Your answer is in because see, this is SI units, right? So if you're so which means that this you will get in watts per bandwidth. Okay, because this is power spectral density. Watts per hertz is what you would get. Instead of bandwidth, let me say this is watts per hertz you will get. But well, not here. Okay, not here, not in the log scale. Here you will get it in watts per hertz. But when you do it in the log scale, if you want to do it in, if you want to get your answer in dBm, this watts need to be converted to milliwatts, right? So what you would also need to do is to add log 10 of 1000 to convert. So how do you convert this watts into milliwatts? You will have to, so to convert to milliwatt, you will have to multiply this by 1000 to convert to milliwatt. And so in the logarithmic scale, in the dBm scale, because dBm is dB with reference to milliwatt, in that case, you will have to add a plus 10 because you're multiplying this by 1000, which means that when you take a logarithm, you have to take a log 1000 also here. Okay, so I will put a plus log 1000 to the base 10 here. This is in dBm. If it is not in dBm, it is just dB, it is fine. This is in dBm. So what changes in ASC2 and ASC3 in the second stage and the third stage? You will have changes in G1. 10 log HU will not change. The noise figure of the EDFA, we are assuming that all the three are ideal EDFAs. So this noise figure is simply 3 dB you can take, right? And you can find out the values of rho AAC at each stage. And we can then find out what is the total PSD, because this noise is something that is additive. So we can just find out what is the total power spectral density. And that is corresponding to PSD1 plus rho AAC1 plus rho AAC2 plus rho AAC3. That is the total PSD. But mind you, when you do this, when you're doing an addition, you can't add in the log scale. So after converting to linear scale, you need to do this addition. But then this total, and then after adding, you can get it back to log scale. Okay, because I can't add powers in dBm. I can add a power and a loss in dBm, but I can't add powers. So you convert that into linear scale, add the powers, and then back to log scale. But this is still again power spectral density per hertz, which means you will get back to log scale. When you get back to log scale, you will get your answer in dBm per hertz. If you look at the question carefully, what you want is write your answer in dBm per nanometer. So noise in expressed in dBm per nanometer would be whatever you got. So let's say noise in dBm per hertz multiplied by the frequency delta F corresponding to 1 nanometer. Right? Now, it is at 1550. So in 1550, you know that for delta lambda is equal to 1 nanometer, the corresponding delta F is 125 gigahertz. This is from our famous delta nu delta lambda conversion. So you can multiply this number, whatever you got an answer, multiply it with 125 gigahertz to get the total power, the noise power at the output. But again, what it's probably better to do not this way because there is again this is in dBm and this is per hertz. So it's probably better to actually do instead of doing this, what you can do is noise in we can calculate watt per nanometer. Directly from this step, you can calculate watt per hertz multiplied by delta F, and then you convert to, so instead of back to log scale here, you can do back to log scale here, so that there's no confusion. So let me repeat. You calculate, after converting to linear scale, you find out the total power per 1 hertz bandwidth, multiply it with the bandwidth, you will get the answer in watts in 1 nanometer. That you convert it back to log scale, 10 log 10 of that answer. That will give you to get your answer in dBm per nanometer. Is that clear? Yes, Devdatta, we are coming to 7 and 8. But this is question 2 now. Now let's move on to 3. And 3 is a related question. If you have an optical filter bandwidth of 0.1 nanometer, the output of the last EDFA, what is the optical signal to noise ratio at the output? That is fairly simple. You calculated in this case, what is the power per hertz. Now you can calculate what is the power per 0.1 nanometer bandwidth. Because here we calculated per nanometer bandwidth, you just have to change it to 1 nanometer, 0.1 nanometer bandwidth. So that is fairly simple. The next question is for a 10 Gbps, this is question 4. For a 10 Gbps, so why are we calculating this? You will realize that the noise can be considerably reduced if I put a filter. This was per nanometer. Here you will put a filter of 0.1 nanometer bandwidth, 1/10 the bandwidth of 1 nanometer. You will see that the noise can be considerably reduced, and then the signal to noise ratio will get really better. And of course, OSNR, how do you calculate? If you have the signal power in dBm, minus noise power in dBm will give you OSNR. Signal power, you already know what is the signal power at the receiver. You have already at 10 dBm power at the receiver. And the noise power is what you have calculated here in the dB scale. So subtract those two, you will get the OSNR. And you'll realize that the OSNR of this with this 0.1 nanometer filter will get you will be much better than without the filter. Then the question is, can I keep reducing the filter? You can't keep reducing the bandwidth of the filter simply because you have the signal which is covering a certain bandwidth, and you're talking about putting a filter to take out this one. But if you make it narrower to reduce the noise, you will lose your data also. So that's not a good idea. Okay, question 4. For a 10 Gbps NRZ intensity modulation system, the receiver is a simple pin diode with the responsivity is given, load resistance is given, electrical bandwidth is given. Assuming that there's no waveform distortion and considering only thermal noise and ASC signal beat noise, find the receiver sensitivity for Q is equal to 7 with OSNR of the input signal is infinite, OSNR is 20 dB, OSNR is 10 dB. 3 cases in the next 3 questions. So what is the information you have? You have NRZ. Again, let's draw this diagram so that we get a visual picture. You have a transmitter. You have 10 Gbps NRZ intensity modulated system. So just go okay. You have a fiber. You have a receiver. The receiver has a diode with a responsivity 1 ampere per watt and a load resistance of 50 ohm. And the electrical bandwidth is 10 gigahertz. I'm using B or delta F interchangeably. Assuming there's no waveform distortion, so no time-related issues, considering only thermal noise, so you want to consider sigma T square and sigma signal AC beat noise square, right? Find the receiver sensitivity. You need to find this, and given that Q is equal to 7. And you have to do it for 3 cases. For the OSNR of input as infinity, then you have OSNR of 20 dB. You also do it for OSNR equal to 30 dB, 10 dB. So receiver sensitivity means what is the received power that you need to have to achieve a Q of 7. Now Q of 7 would mean BER of 1E minus 12. So you can now, it's the same relation that we have seen before. You can say that your Q is, I1 minus I0 by sigma 1 plus sigma naught, and assume that I0 is equal to 0. Ideally, there's no power in the 0 bit. So you can say that I1 minus sigma naught plus sigma 1. And the difference here is that because there is an EDFA, sigma naught is just the thermal noise in the 0 state and noise in the 1 state. So this is thermal noise. And sigma in the 1 state is, so this is thermal noise, plus sigma in the 1 state is thermal noise, plus here you have an amplifier. So you can do the signal AC beat noise. You would have an amplifier noise here, but that is only AC. There is no signal here. So so what happens is, in this case, there is no signal here in the 0 state, so you have only the noise. So here you will have only AC beat noise. And in the question, we have made it very clear that don't consider AC beat noise, consider only the thermal and signal AC beat noise, which means that in the 0 state, you have only the thermal noise, whereas in the 1 state, you have the signal AC beat noise as well as the thermal noise. Okay, so you can, that if, I1 is what power, I1 is a current in the 1 state. And how do I find the current in the one state? RD times power in the one state. And in terms of average power, I can write it as twice RD times average power, because this is what we've been doing earlier also. Okay. And then I can substitute this thing here. And what is not known to me? The only thing that is not known to me is received power. Okay. So with this, of course, this signal AAC beat noise will also have received power. So it is not a very straightforward equation to solve. But what you can you will realize is that the contribution. So you can work it out. You can work it out under for example, in the first case where you have OSNR is equal to infinity, it implies the signal AAC beat noise is 0 because there's no noise. And when the OSNR is 20 dB, it means that the signal AAC ratio is P received divided by the noise power. The noise power is P received by 100, simply because OSNR is nothing but the signal power divided by noise power. So you can calculate the noise power in each case, and then that will help you to calculate the signal AAC peak noise. Okay? And similarly, in OSNR is 10 dB, this will be P received by 10. So that's how you solve the next 3 questions. And the last question which Devdatta was asking is question number 7. And the question says that you have a Gaussian pulse. Let's draw this Gaussian pulse as a function of time. This is power P naught. It's defined as full width at half maximum is root of 8 ln 2 T naught, where P of T is defined as a Gaussian, which is P naught exponential minus T square by T naught square. I mean, we have done the job easier for you to find out the FWHM. This is 1 by E width. This T naught is 1 by E width. That is a width at which the power falls to 1 by E of the peak value. That's different from full width at half maximum. Full width at half maximum, when this becomes P naught by 2, is given by this relation. Just give me 1 second. Sorry about the break. But this is something that we have given for you. I mean, this is not a complicated relation to derive, but we have given this just to make things simpler for you. The question is now, assuming that the return to zero pulse is Gaussian shaped like this, what is given is typically full width at half maximum is given to be 50 picoseconds. So from that, you can find out what is your T naught. That's easy. Given that gamma is 2 watt inverse kilometer inverse, right? Loss is 0.2 dB per kilometer. You want to find out what is a nonlinear phase accumulated over 80 kilometer, right? So you want to basically find out what is phi NL at Z equal to 80 kilometer. When the peak power is P naught is 1 milliwatt. That's the first question. Now, whenever there is a loss, we can. So what does it mean? It means that the power as a function of position. I think we are discussing this in the class also. This is power as a function of position. This P naught, value of P naught, as the pulse propagates through the fiber, it decays at the rate of 0.2 dB per kilometer. So at the end of 80 kilometer, right, your power is just P naught e power minus alpha z, where z is equal to 80 kilometer. Now we know that the nonlinear phase is, we have derived in class that this phi in L is equal to gamma P in L. But the only thing you need to change is that instead of this L, you need to change it to effective length. The reason being that if I just take it as gamma PL, this P is a continuous function of position. So the easiest way to take care of it is to say that instead of considering propagation over the entire length, you imagine that I can represent this propagation up to an effective length L effective, for which the power is constant. So the area under this red curve. So how do I find the L effective? The area under this red curve and the area under this black curve, if I equate, I can find out the L effective. And that we have found out in the class that this is gamma P in 1 minus exponential minus alpha L divided by alpha. So L effective for this problem turns out to be, if I calculate this for 80 kilometer and with a loss of 0.2 dB per kilometer, this number turns out to be, I think, 21.2 kilometer or something like that, about 21 kilometer. And the reason I'm telling that number is because you will now say that you don't have to really consider the propagation through 80 kilometer. Its effect is represented by propagation through about 21 kilometer. Approximately. This is not an accurate number. You have to calculate the accurate number. Okay. And once I have this, you can find out what is the phase accumulated. The next question is, the answer is in megahertz and gigahertz. So the question is not phase accumulated. So there is a correction in the question. It is not nonlinear phase accumulated. It is you have to calculate the frequency spread due to SPM and XPM. So thanks Devdatta for bringing this up. The question is to calculate the frequency spread due to SPM and XPM. Okay, so how do I now calculate the frequency spread? The frequency spread is derivative of this, right? So I have delta omega, in fact, twice the derivative of this. So this is minus gamma dp by dt. Well, we know that this we did in the class also. We know that the instantaneous frequency omega is d phi by dt, right? And I know that the power. So what happens really? You have this pulse shaped this way, and as the dp by dt, so the dp by dt becomes it's 0 here, it's 0 here again. So it's 0 here, it's 0 here again. It becomes maximum in this region, right? So that is the point where the frequency change becomes maximum. This we discussed in the class, right? So you can calculate the dp by dt and the maximum value of that, because you know that P equal to P naught e power minus, you have that P equal to P naught e power minus T square by T naught square. So from that you can calculate dP by dt and calculate the maximum value of dP by dt. Okay, and once you know the maximum value of dP by dt, you can calculate the chirp as in fact, this negative sign does not matter. The derivative of the phase as it's a derivative of this quantity, right? The derivative of the phase. So that is frequency. So this is gamma, and the maximum frequency change is gamma del P by del T, maximum of that multiplied by L effective. L effective is something you had calculated earlier. Okay, so but actually this is delta omega, because if I write this expression e power j omega t minus beta z, and if I say that this is my phase, if I take the derivative of phase, I get omega. So if I want to have delta F, I should actually, so I should say delta F maximum is delta omega maximum divided by 2 pi. But we know that the frequency content actually maybe increases here and then maybe decreases here. So the change in maximum change in frequency or additional frequency that you get is twice delta F max. So you can calculate, once you know the delta F max, you can calculate twice delta F max. You can do this for 2 power levels, only the numbers will change. Okay, so the question should be, what is the total frequency spread due to, there's no XPM in this case, it is just SPM. Instead of total phase, the question should be reworded as total frequency spread. So thanks for pointing this out. I will send out an email tonight itself. Is there anything else that I can help you with? Are there any other questions? If there are no more questions, we will stop the session. Excuse me. Okay, I don't think there are any more questions, so we will stop the session and see you next week.